Who our first speaker is, and it's Roger Anderson. He's going to talk about omissions in special relativity. Okay, Roger, we'll give you a 5-minute signal.
Thank you. Right.
And it's 5 minutes.
Thanks for letting me give this talk. It's called Omissions in Special Relativity. And I've got my friend over in Serbia, Professor Dragoslav, who helped me a bit with this. Right, so the outline of the talk is, it's going to be different to what I originally planned because I was talking to Richard Amoroso and he suggested calling it omissions instead of mistranslations. I'm going to say mistranslations. So I'm going to try to talk in terms of omissions and probably additions in the text and special relativity. And I might now and again.
It's just coming. I overtook him just.
Yeah. Bit too early, probably.
Yeah.
He needs coffee to keep going. And now and again, I might slip back to calling it mistranslations. Okay.
You can try fluctuations.
Fluctuations.
Accretions, perhaps.
Okay. Right. Quantum jelly. Last year, Jeffrey gave a talk on quantum jelly, and it prompted me to think of something I'd read decades ago in a popular science magazine called Science Digest, which unfortunately is not around anymore. It was dealt with the issue of trying to understand science at a popular level, such as the mystery of light speed, in vacuum being constant. How could light change its speed through different medium and still be said to have a constant speed? So let's just move this a bit. Okay. Next. So the science.
Roger, could I just suggest you move the laptop over because you're in the way of the image?
This image?
Yes, but so if you move your laptop over to the right, when you look at it, you won't be, yeah. Thanks.
That is better.
Good.
So the magazine had a question asked, and it was to do with an earlier question. It says, you explain that light travelling through a dense medium excites the molecules therein, causing them to radiate light energy. The time lag involved in the molecules being excited and emitting a new photon effectively slows down the entire wave packet. If this is the case, then what accounts for the strange phenomenon of the being light resuming its original speed after leaving the medium through which it's travelled? That's all the question they asked. And the magazine gave a picture, and it reminded me of Jeffrey's quantum jelly.
I've got the bottle of it.
And this is like the photons come in, get absorbed by an atom, excite the atom, then get re-emitted, and then so on. So it's going through this medium, and the light's going slower through it. Out here, say, it would be a less dense medium, and light be faster, it comes through here, and it's delayed by being absorbed and re-emitted. So, the magazine New Science staff replied, in modern quantum mechanics, light is thought to be composed of particles called photons that always travel at the speed of light in a vacuum. When a photon strikes an atom, it is absorbed, causing some of the atom's electrons to jump to an unstable higher orbit or energy level. When the electron falls back to its original, more stable orbit, a new photon is emitted, also travelling at the speed of light. So you've got a train like that, and this is causing a delay as the photon gets encounters all these molecules and atoms. So when you think about it, basically in Einstein's 1905 paper on special relativity, he wasn't considering quantum effects. Quantum mechanics was not formulated until later in the 1920s. It is fairly well known that special relativity is a classical theory in the sense that it does not consider or include quantum mechanics. If you had light travelling through a vacuum, which is idealised as devoid of matter, then there's no quantum effects of interaction with other particles happening. I think the best way to describe it is Einstein, 1905, was dealing with a classical vacuum devoid of any matter particles, but quantum mechanics would consider what we call a quantum vacuum that obeys Heisenberg's uncertainty principle and has virtual possible particles that pop in and out of existence. So, 1905, Einstein's vacuum would be a classical vacuum, and there's no particles popping into and out of existence which would slow the light down. So you've got two types of vacuum. But there are problems. When you're considering quantum mechanics, then you're bringing back a type of medium, ether, and that was something special relativity was excluding. So the quantum vacuum, or the quantum jelly, is sort of like a vacuum, like an ether. Special relativity is making the omission of quantum mechanics, and that omission is including omission of ether with its preferred frame. So the theory in 1905 was saying we're not going to include an ether in it. It's not a case of there's no ether. It's a case of just not going to consider an ether. With Michelson-Morley experiment and other experiments, Einstein's solution of special relativity seems to be an omission of these and other things from what's being dealt with in its mathematics. And so then these omissions are something that gets added back in later with quantum mechanics. So you've got special relativity, it's dealing with an idealised classical vacuum, and if you include quantum mechanics, you would have to say, well, there is the ether back again. So after not including it, then include it back again. So it's not a case of proving there's no ether, but more a case of just ignoring it temporarily for the sake of certain experiments, which is quite different to how it's usually presented. So now let's consider how special relativity gets its mathematics. What you have is sort of like a light clock, where the light is bouncing between mirrors, and when the clock is moving, that appears to be zigzagging. So that is like, you can consider that as a point particle moving up and moving down, and it's still a point particle and it's zigzagging. And that would be an idealisation. You consider it like light represented by a point particle bouncing between mirrors. There are some texts on relativity that go all the way back to basics, such as pointing out about the point particle. This is an example, Ray Skinner, Relativity for Scientists and Engineers, and he points out the idea of the point particle, but not all texts are mentioning this. So, both quantum mechanics and Einstein's relativity are built from this idea of point particles, point particle idealisation there. So, that's not often pointed out. But according to the mainstream, there's problems joining Einstein's relativity, general relativity, with quantum physics. So they're not really dealing with point particles properly. You've got something like a classical point particle and a quantum point particle, and they're dealing with those things slightly differently. It's the way Einstein deals with point particles seems peculiar, because you're treating special relativity as a classical theory, so you call it a classical point particle. There are some problems with how Einstein deals with point particles and the way quantum physics deals with point particles. Right, now we get to Einstein. He never provided references for his paper on relativity, and I've got the book on that, showing Einstein's relativity there to look at if you want to. And according to Max Born, he says the paper on Einstein's relativity contains not a single reference to a previous literature. It gives the impression of quite a new venture. If Einstein had provided references, then it would be easier to check the context from what he's talking about. So it's another omission from Einstein. Max Born goes on to explain if Einstein's relativity, bracket, that's what he's talking about, gives you the impression of quite a new venture, but it is of course not, as I've tried to explain, not true. So really, Einstein's relativity, 1905, is still building upon what had been talked about in the physics literature before him. Unfortunately, he wasn't providing references. Right, this issue of omissions, the omissions I've pointed out so far, and other things like it, was going to be addressed in the physics conference of 1955, where Einstein was told he was going to ask about what influence Poincaré had on him. There were questions raised by the British book on the history of the theory of ether and electricity. Unfortunately, Einstein did not live long enough to attend the conference, so the influences on Einstein is not properly resolved as far as I'm concerned as to the context from what he was working from. So Einstein provides no references. They were going to try to sort that problem out, but unfortunately Einstein then dies. So it's left as a mystery of how Einstein got to where he was. In Einstein's formulation of special relativity, we need his starting point, and he seems to have mentioned Newtonian physics in his 1905 paper, and translation from that is at that site. And the official translation seems to refer to that 1905 paper as on the electrodynamics of moving bodies. In the German, you say, Einstein's saying all this, and that can get translated as there is a coordinate system in which the Newtonian mechanical equations apply. We call this coordinate system a linguistic distinction between later introduced coordinate systems and the definition of the dominant system. So, that normally gets translated as, let us take a system of coordinates in which the equations of Newtonian mechanics holds good, which seems okay. Einstein seems to be starting from Newtonian physics with his paper on relativity in 1905. But then there's a footnote that gets added in the English translation, which is not in the original German version. So he says this, let us take a system of coordinates in which the equations of Newtonian mechanics holds good, but then there's a footnote which gets added. It's not in the original version, and it's also not in the Serbian translation from the German. So there's various versions of translation of Einstein's 1905 paper. Based on what seems to be the official version of the English translation of the 1905 German paper, it was published by Newton and Company in 1923. So the footnote has been added by the translator to try to make sense from what he's read in German. So from the German we have near enough from saying that, but the English version has the footnote, i.e. to the first approximation. Now I contend that's two different theories. So the German theory is a different theory to the English theory. I nicknamed, and that's two different theories. That's two theories. I contend that the original German theory is probably what's really meant, and the English version, based on using that footnote, is probably wrong. That footnote's probably wrong. That's probably not referring to the correct theory. So, now going by Born, which you said earlier, that it's not a new venture. It means that what Einstein was doing, he was working from what others were doing before him. Therefore, any deviation from how others before him were dealing with point particles must most likely be a mistake. So, we'll back to point particles again. If Einstein's dealing with point particles and he's doing something different to what other people before him have been doing.
Needs to move this board because it blocked this
In
screen.
front of the door, perhaps, where it's. Can you put it?
I've got it lined up from what.
Oh, right, okay.
Therefore, any deviation from how others before him were dealing with point particles must most likely be a mistake. And we're presented with equations such as this one, and told that as v tends to 0, then this approximates to Newtonian physics. I'm going to drop the deltas and write it as that. Deltas are just being used to emphasise it's about time intervals. So this equation is supposed to be Newtonian physics when v tends to 0. Now, if we go back to the light clock, the point particle bounces up and down when it's stationary and zigzagging when it's moving. When the light clock is stationary, distance is ct, and the thing to note is what is being dealt with is a point particle moving the distance d in time t with speed c, so that the distance equals ct. And when it's moving, what we can form from the zigzag is a Pythagorean triangle, and the hypotenuse is equal to c t prime, and the horizontal is vt prime, and the vertical is that. But the thing to note is we're still dealing with point particles.
Roger. I think you can move that back like Omissions and still have it in the same line. So
What we're doing now?
no, on the drawboard. So you see by the door there's 6 on the back tripod.
I'll do it.
Just hold it really on. Show me a line if you can.
Yeah. Well, the problem is, Roger, you are actually standing in front of your own slides the whole time, which makes it impossible to see them. And yeah, that's better. Where you are now is great.
So the equation that we form is based upon point particles, and what is to note is that the point particles are still obeying Newtonian physics, which later goes into Boskowitz. Newtonian physics later becomes Boskowitz theory. So you've got point particles still obeying Newtonian physics. So the claim that that equation reduces to Newtonian physics as v tends to 0 is false. The equation itself is derived from Newtonian physics and is hence a Newtonian equation. That's a Newtonian equation. That's not calling it a special relativity equation. Well, no, it's Newtonian physics, the Newtonian physics derived equation. There is no reducing to Newtonian physics as v tends to 0. The equation is already part of Newtonian physics. So what they're telling you is wrong. The context of how Einstein's relativity is to be understood has been falsely presented. I'm saying relativity has been falsely translated. And this is based on nitpicking. So now an example of a maths problem in Einstein's paper. In this paper in 1911, he has this equation. was such publications as by this person, Cheng. He has a 0 there. You've missed that 0 there. So what appears to be happening is they're just treating Einstein's papers as historical papers and leaving the mistakes in them. So I contend there must be numerous problems in translation of how relativity has been presented to us, and also numerous problems of mathematical mistakes in those papers. And all those things have been allowed to be left uncorrected for these past 100 years. So, trying to make sense of what we're left with. This is a reminder from the direction I'm coming from. I'm working from Boskovich's theory, and this is a book I translated from Professor Stogovich. What happened with Newtonian physics, it got further developed in the 18th century on this issue of point particles. So Newton would have been dealing with point particles as only being attractive. Gravity was the only sort of force he was considering. And further development would be to consider these point particles as what they're doing when the force is both attractive and repulsive. So Isaac Newton founded classical mechanics on the view that space is distinct from body and that time passes uniformly without regard to whether anything happens in the world. So for this reason he spoke of absolute space and absolute time. But in the continuation of Newtonian physics under Boscovich, there was further development on relationships between absolute and relative space and time. Under Lorentz, I think he was talking in terms of local time. So this equation, which is derived from Newtonian physics, you would be talking about that in terms of local time. And I think Lorentz was talking about that. And we go back to Einstein. Einstein didn't have a chance to clarify what he was doing because he didn't attend the 1955 conference, but they would raise these issues with him. Einstein was dealing with classical point particles in the sense that he was ignoring quantum effects. So, 1905 paper based on classical physics. So it's classical point particle, but he's dealing with no ether. And that was not dealing with quantum physics. And what we got in the history books, they point out there was a Newtonian research program. This person, Smith, points out in his book, Newtonian research program of 18th century physics has Newton's three laws and this is gravitational as its hardcore. Boscovich was part of that. It was a continuation of Newtonian physics. Right. So Alice Caprice points out Einstein never became fluent in English, either written or spoken, in his day. The language of science was German, and there was no need for him for English until he was in the United States at the age of 55. If he was asked to speak formally or to write a paper, to write a letter or an article, he would first make a draft in German, and then a colleague or secretary would translate it. So I'm thinking in terms that when we got these translations in English of what Einstein's talking about, maybe he didn't actually check that. He's relying on other people to make sure the English translations are correct. So, back to the issue, when Einstein first talks Newtonian physics in his paper on relativity, it should be translated as, let us take a system of coordinates in which the equation of Newtonian mechanics all good, and without the footnote. The footnote is a mistake. The context is now that Einstein's relativity is being dealt with in the context of Newtonian physics, and the thought that it is otherwise is a mistake made in translation. Now, given that both Einstein's relativity and quantum mechanics are dealing with Boscovich theory points, we have a common link between them. Of course, there are other problems with translation of Einstein, but we have a general outline of unification between relativity and quantum physics. There are other issues in the Newtonian research program. Because a lot of other things misrepresented, for instance, in order to simplify Newton's theory of light, it is often portrayed as solely a particle theory of light, when actually it has particles that have wave properties. Thus, the Newton particle theory of light versus Huygens theory of light was an artificial misrepresentation. I think in the context of Boscovich, you would have a particle under the influence of a field force, and under Bohm's description that would be a particle under the influence of a pilot wave. So my conclusion is it has not been properly appreciated the development of Newtonian physics, especially building on the concept of point particles. So your classical point particle under the context of special relativity, and it's just ignoring the ether. There's a type of ether, you add it back and you've got a quantum point particle. There's a more unified physics narrative that goes roughly like this: Newton, Boscovich, Einstein and Bohm. There are of course other people such as Galileo and Maxwell, but what is generally missed out from being taught to physics students is about Boscovich and Bohm and so on. I could finish here, except I would like to cause grief and talk about what I consider a new problem arising in physics. There's more problems. I think there's a new type of problem arising in physics. And it's a question of, did Einstein actually say what he's claimed to have said? There's a well-known saying that Einstein claimed that introducing the cosmological constant was the greatest blunder he ever made, but did he actually really say that? Mariout here, at that side there, is querying that. According to Mariout, there's nothing in Einstein's writings that he actually said that, and the quote goes back to Gamow, and according to him, Gamow is a notorious joker, so maybe he's taking the view maybe that was just a joke. How do we decide what Einstein actually said? Do we have to go solely what he wrote, or do we allow what he supposedly said to other people to stand as being legitimate? So how do we accept anecdotal evidence? A lot of the evidence being presented to us now is how to understand Einstein's relativity is anecdotal. It's supposedly what he said to various people when he explained relativity to them. And when we go back to Huygens, we have problems with making sense of anything. The problem has affected Ivana Trump. She's quoted Einstein, and now she's been accused of misquoting Einstein. So there's a lot of quotes from Einstein out there. Did he actually say it? We don't know. Einstein said, thank you. Einstein said, since the mathematicians have made the theory of relativity, I do not understand it myself anymore. I hope that's a true quote. I don't know whether that. I got a reference to him saying that. So I think that's indicating to some extent the problem of translation from German into English being transmitted back to him.
I think it's a problem with mathematicians.
And them as well. So it's a problem with mathematicians, but they're translated from German into English. The people speaking English have then got a slightly different understanding of relativity of what Einstein has, and they're doing maths based on that. So the problem is being fed back to him, if that quote is true. There's a translation problem from German to English is much more subtle than, say, from German to Japanese, where it's probably Einstein's relativity got translated into being a theory about sex. Sex theory that made it very popular from the Japanese supposedly at the time. Was the theory about sex, yeah. So you've got massive audience. So the final thoughts I want to leave you with is relativity might have been something other than what we commonly think it was about. Thank you, goodbye.
I mentioned that there is another translation into English of Einstein's complete papers.
Certainly is.
A man called Krakauer, who I know well, got tired of the pomposity of the standard edition and it going on forever and ever to produce it, and also the incredible price of it.
Yeah.
And he produced a translation of all of Einstein's German papers into English. Can I write his name down? Krakauer.
Okay.
He's actually American, this man. Al
I know him too.
Krakauer. So you might want to consult that to see what he makes of the same texts.
Okay.
I want to put in a word here for the official translation. It's the work of many hands. It's the fact that it took a very, very long time to appear would seem to me to be good circumstantial evidence that they were paying, that John Stachel and his many colleagues, Dennis Lempel, who's now the head of the Einstein Papers project based in Pasadena, were paying very, very scrupulous attention to getting the translation correct.
Yeah, John Stachel is a good guy, no question.
Yes, well,
I agree on that.
completely agree on that.
But
So
I'm just
I think,
saying what Krakauer said, not what I said.
yeah, okay, fair enough. But I think that goes to some of the points that Roger was making. I mean, these are not questions that have not been gone into in vast detail. The source of the quotation about Einstein, the mathematicians, now the mathematicians have taken charge or invaded the theory of relativity, no longer understanding myself, is, I understand it, actually from a conversation with John Stachel, a direct response to his encounters with Cartan, with A. Cartan, and was a response to what became Newton-Cartan theory. He was saying he basically didn't understand Newton-Cartan theory. Interesting if true. And the quotation about, the other one you mentioned about that you said you wasn't sure whether anybody's ever sourced it properly. I'm no expert on the Einstein text, but I understood that the quotation you gave on your second or third slide, I'm sorry, it slipped my memory now which one it was, sorry, is there any chance you can put them up again, or are they gone? All right. Oh, okay, in that case, let's keep it for the interval, that's okay. Anyway, I understood that the context of that quotation was in fact quite well known and quite well established.
So, I need time for any couple of quick questions.
Yeah, there is a Russian relativity. There is a Russian, not only English, not only German, but there is a Russian relativity.
Russian translation.
Russian translation, I mean. And I did not agree with relativity at all, at Russian too. And what about you? I don't understand. I agree with English.
Are you supporting?
I supported this theory, or no?
What relativity?
Yeah.
I just research going where what search takes me.
No, I don't think he's saying whether he supports relativity now. What he's saying is that what Einstein said and what is quoted is not the same thing. And it makes a slightly nuanced and slightly different aspect to the theory. Is that correct?
Two problems. The first problem is that all Einstein's thoughts
Well, no, before. He basically, like you said before, that he was basically based on other authors and didn't. But also his main idea was that that's how world is made, that's in solid. Do you agree with that?
But I think the theory of relativity is the model only. The model.
Just one of
In any case, he actually published the title of his first paper on relativity is about electrodynamics, as though it's part of a tradition already in existence.
Yeah. But he didn't reference anything, which makes it difficult to see, is he making a mistake based on what he's reading, whether he's doing something new.
How can you write a paper without writing about...
Well, you're talking about more than 100 years ago, standards have changed.
Yes, a great deal. There were lots of papers published without references at that time.
Also, the paper was published without refereeing by...
Refereeing didn't become common for scientific papers until the 1930s. It was quite normal for papers to be submitted to journals and published unrefereed until the mid-1930s, or even later in Europe.
But because he became famous, it's kind of important what he said. And so it would just be another paper which everybody ignored until it became famous. Now we look at it, so it's not clarifying things properly.
Okay, can we thank Roger again? Because our next speaker is Tommy.